Here we look into the process of preparing optimum creams. So we'll apply the same knowledge that we've learned before in terms of the optimization process, factorial design, and how to choose the right variables. I suggest to you, if you're not familiar with those concepts, just go back and check the relevant videos which are on, especially which deal with the concept, the original concept, optimization and variables. The question is what is a cream? So in general term, the any cream is a mixture of oil and water to form an emulsion, and this clearly here needs to remain mixed. It should spread easily on the skin, so absorbed without having any sort of greasiness, which might not be ideal. There are two types. So you could have the dominant phase as oil, or it could be the opposite, as the water phase is the dominant. The most common type is the where the water is the main part, which is the oil in water, and that's often preferred because it feels light. The other type, which is often very moisturizing, is the water in oil. And the reason why it's very moisturizing because it keeps the moisture inside the skin. And that is very important to ensure a healthy skin in many conditions, especially dry skin conditions. This animation shows how the both types of emulsions, which are creams when the viscosity is high, are formed. So in both cases, you will find droplets of either oil or water. If it's an oil in water, uh, that means the oil droplets are suspended, just like the one on the left. The opposite is correct when we have water droplets are suspended in an oily phase. And in both cases, those are emulsions and both can lead to the formation of a cream. There are challenges with forming good creams. So here, as is shown in this animation, these are common problems that can happen. So as you can see here, creaming is where you start to see the oil separation, and that just migrates to the surface. The opposite can happen as well when you have sedimentation, and that just because of the gravity, the components they can just separate. Often is the water the aqueous phase. What can also happen is the flocculation when there is poor stabilization by surfactants. So the dispersed phase get just um, it gets flocculae forming small flocks, and that could be an intermediate phase before full separation. Finally, the dispersed phase, they can just come together and coalescence, so they can completely merge, not even as floccules. And this is clearly is another reason for instability, because that will be followed by complete separation. Something really useful we use for matching the surfactant to the oil phase. And this is the hydrophilic lipophilic balance, HLB system. And it's purely based on the balance or the ratio between the hydrophilic property and the hydrophobic of the surface active agent molecule. If you look here on the top left, this is how the surface active agent or a surfactant molecule is represented. So here you have a carbon chain, which is indicated by the yellow branch, and at the end you get the hydrophilic part. Uh, and that basically the blue circle, that is the part which likes to be associated with water. So the ratio between both of them, that gives the surfactant a value which is the HLB value, and that goes from very low, and that means it's more hydrophobic or lipophilic, loves the oil, and goes all the way to high values where it likes to be, which has more like hydrophilic nature. And you'll see the way these are used, it really depends on the HLB value. So it depends on the classification of the surfactant. then that will allow us to choose the ones which will be ideal for the purpose we want to use. So for example, a smaller HLB you would use for application, for example, in water, in oil, or anti-foaming. And as you go up, go use wetting agents, oil and water, formulations, when you go towards that HLB value of 12, and when you go higher, detergent and solubilizers. So generally speaking, this is the region at higher HLB where where we'll use those surfactants for oil in water, um, creams or emulsions. Similar to the previous animation, in this case, it's just to give you some classical examples. So exactly the same category where you have the HLB value or HLB scale. And it gives you things like span 80, span 60, tween 80, tween 20, NSLS. Those are classical examples of surfactants that are used to form emulsions. But the idea, you just choose which surfactant you want to select to stabilize your emulsion. How do we make creams? So this is the process where you do the actual mixing of the oil and aqueous phase. So the first step is to heat the oil phase, and in many cases you will use a high temperature around 70 to 75. And in many cases you add water to oil slowly, and this depends on the viscosity as well. But you depending on which one is the dispersed phase, which one is the continuous phase. You add the water to oil, and slowly, um, and you start to stir the mixture, and you add them at a slow rate. And then this followed by high speed mixing to make sure we end up with good and uniform distribution of the surfactants and the formation of smaller droplets. And this is carried on until the mixture starts to cool down to make sure we have a good homogeneous mixture. And this is explained here into the animation, because you'll have larger droplets and eventually end up with the smaller ones. The surfactant helps into breaking those um, into smaller droplets because it lowers the interfacial tension. And with the mixing, you are providing energy to the system, so you're breaking those into smaller and smaller. Surfactant will coat those smaller droplets and will help stabilize them and forming this um, kind of barriers or across or bridges, more or less, lamellar faces. Lamellar faces aggregations of the surfactant molecules, and that enhances the viscosity and gives the structure, the cream, its unique structure. So what are the variables that we can change to ensure good surfactant is produced? The first variable here we suggest is the emulsifier concentration or the surfactant. Emulsifier is the same as the surfactant. And in this case, we decided to vary this by ratios to 5-8%. In many cases, the amount should be even lower than this, but this is just for a demonstration reason. The oil phase can also be changed. And here, let's for example, we are preparing an oil in water cream. So clearly here, the maximum should be much lower than the aqueous phase, and this is here in this case is 35%. So you see the ratio we have varied is 15, 25, and 35. And then just a reminder, this should have equal distances as we stressed that in previously to ensure we have robust factorial design. More oil, that means there's a richer cream, but then that means you've got to have more emulsifier, because as we mentioned, they will coat the droplets and prevent instability problems. So the question is, how do creams deliver drugs to the skin, or even when they are used to moisturize the skin? The first step is, of course, absorption to the surface. And the rate limiting step is the penetration into this cement-like structure, which is called the stratum corneum. If it passes through, then it will go through the epidermis and it goes down all the way into the dermis layer. If it's a drug to be delivered, then it goes into these red capillaries, just this to indicate that we have absorption process. Just like as mentioned, in many cases, you want to provide a cream to treat topical conditions. So you want to make sure that you have your system have good moisturizing effect for the skin. Pharmaceutical creams are often exhibit pseudoplastic um, kind of pattern or a trend, and this is explained here in this graph on the right. These are the common ways how the materials respond to shear stress. Basically, when you apply a stress on the material, it could be related to the shear rate. So if you apply some kind of rate, the stress or the response to this will be similar. It's be linear. What you could have is a drift from this Newtonian behavior, which is the dilated kind of behavior, and this case is exponential. If you look at the red line, this is exponential. Basically, if you increase the shear, then that will increase the viscosity. And the opposite is with the pseudoplastic. If you increase the shear on the cream, then that will reduce the viscosity. So this is the kind of behavior we often see with the creams. So it's a pseudoplastic behavior. The one which is a more like a way we can test this is to apply some known amount of a cream, and we apply some um, like a spreading tool to measure how much of the cream will spread, and this is often related to the viscosity. Because when you apply shear or you apply this stress on the material, it will affect the viscosity, and that will reduce the viscosity by certain amount or certain value depending on the cream that you have prepared. So this is the spreadability test, and this is directly related to the viscosity of the cream. These are common quality tests that are used to assess the formed creams. The first one, which we mentioned, is the spreadability, and this is related to the viscosity as well. And that often gives you an idea how the cream is doing when spread on the skin. And using this test, you will measure the diameter spread under fixed weight. You can also do a centrifugation test, and using this, you centrifuge the formed cream under, for example, 3000 RPM, and you check if there are any signs of separation. Viscosity can also be checked, as we mentioned, and that give the measure of the thickness of the cream. And then like we said, the pharmaceutical creams should have a pseudoplastic behavior or shear thinning effect. The pH must be skin compatible around 5.5 and should remain stable. And finally, stability is essential, so no separation after weeks of storage at fixed conditions. So what we would expect here is if we increase the amount of the emulsifier, then we often should end up with more stable cream. But on the other hand, that might affect the consistency, and it may affect the texture of the cream. So that's something we need to check. The oil phase, if it's increased, that will feel richer, but might be harder to stabilize. So we have to give attention to the amount of the emulsifier. The interaction between both the oil phase and the emulsifier, uh, that means we will have to keep an attention on this part, because that means we'll need to more, like I said, we increase the amount of the emulsifier. So too much emulsifier, that means it can also lead to some problems because it might irritate the skin, especially when using uh, cationic or anion, or in many cases anionic, such as sodium lauryl sulfate, that could lead to irritation of the skin. The idea is, as is shown here in this animation, you find the sweet spots. So you find where the best conditions are reached to give you the optimum level.